Hello again. Today we're going to be looking at one of the most important concepts in physics, and that's Faraday's law of induction. And basically it's the idea that a change in what's called the magnetic flux going through a loop of wire or a coil of wire with many loops will create a current within the coil. So let's start our lecture and we can see how this looks. So before we talk about a change in magnetic flux, we need to define what the magnetic flux is. And it's just like the electric flux in the sense that it's the component of the magnetic field vector that penetrates through a surface multiplied by the area of that surface. And again, like electric flux, that could be tangible physical surface, but it doesn't actually have to be. But otherwise, it's very similar that dA is exactly what it was with the electric flux. And here you're taking the dot product. Instead of with the electric field, you're doing it with the magnetic field. And you're integrating. And so that's the general version. In the special case where the magnetic field is uniform and the surface is flat, the magnetic flux is simply equal to B, the magnitude of the magnetic field, times A, the area over which it's crossing, and the cosine of theta. And again, theta is defined as the angle the magnetic field vector makes with a line that's perpendicular to the surface. Magnetic flux, unlike electric flux, has a special unit in SI units. It's called the Weber. The Weber is equivalent to a Tesla square meter. And one important property of the magnetic flux, and so this is the magnetic equivalent of Gauss's law, is that if you calculate the flux over a fully enclosed surface, and again, it doesn't have to be a real physical surface, it could be any surface, real or imaginary, that you could construct that's completely enclosed, the magnetic flux is going to be zero over that closed surface. And the reason being is that unlike with electric fields, where you can have isolated positive and negative source charges, with a magnetic field, you can't have a positive without a negative. So with any closed surface, the magnetic field is going to go out for part of it, and it's out of part of the surface and in from another part of the surface, and that the over the entire surface, they cancel each other out, and the total flux is zero. And that's an important property that comes into play when we talk about Maxwell's equations, which we'll not get to in this semester. But if you take Physics 3 with us, you'll definitely see it. So Faraday's law of induction concerns the magnetic flux through the plane of an enclosed loop of current. And it could be a circular loop, it could be a rectangular loop, it could be any sort of arbitrary shape, as long as it's enclosing a certain amount of area. And so we're interested in the magnetic flux through that surface. And what happens is, and this is something Faraday observed, and he was able to generalize that any change in the magnetic flux will cause a current to show up, or will cause there to be a current in a loop of wire. So basically, it'll make the electrons move. And this is something that you can measure, and you can figure out the magnitude, and you can figure out the direction. We'll talk about the magnitude right now. And we'll talk about direction in a couple of minutes. But the magnitude of the induced EMF is equal to the total number of turns in the coil, which is capital N, multiplied by the rate of change of the magnetic field. So the magnetic flux, excuse me. So the more quickly the magnetic flux is changing, the greater the induced EMF you'll see, and the greater the current you'll see through the loop as well. And something to keep in mind is that there are basically three ways the magnetic flux can change. So if we go back to here, you look at B times A times the cosine of theta, you can change the magnetic flux three different ways. You can change the magnetic field going through the wire, you can change the area enclosed by the wire, or you can change theta, the angle at which the wire makes with the magnetic field. And the theta is actually important because when you talk about AC generators, what you're doing is you're rotating a loop of wire through the magnetic field, so it's theta that's always changing, and what that results in is as an alternating current with the direction shifts back and forth and back and forth. So with that, let's go to some examples. So this is example number 1 for chapter 29, if you look at the problems. The magnetic flux through a coil of wire containing 2 loops changes at a constant rate from -58 Webers to 38 Webers in 0.42 seconds. What is the EMF induced in the coil? So let's go to the whiteboard. So again, we have delta V is equal to, and this is the magnitude of delta V. Like I said, we'll focus on direction a bit later. So that's N times the change in the magnetic flux with respect to time. So what do we have? So we're told the coil of wire contains 2 loops. So capital N is simply 2. At a constant rate, so we're given the change in the magnetic flux. It's -58 to 38, and then it's 0.42 seconds. So and it's at a uniform rate, so we don't need to be concerned so much with the derivative. We're just interested in the change. And so that's -58 to 38. So the change is 38 Webers minus -58 Webers, or simply plus 58 Webers. And so that equals 96 Webers, and that's positive. And again, direction is more or less arbitrarily defined as far as, I mean, which direction is positive and which direction is negative is more or less arbitrarily defined. But the relationship between the direction of the current and the direction of the magnetic, or the change in the magnetic flux is not arbitrary. And so then delta T, or dt, is equal to 0.42 seconds. So we've got all the information we need to solve this problem. So that's 2 times 96 Webers divided by 0.42 seconds. And that's going to give us the induced EMF in volts. And so we figure that out. And that gives us, to 2 significant figures, 460 volts, or 4.6 times 10 to the 2 if you prefer that. So that's the first example. The second example says a 22.0 centimeter diameter loop of wire is initially oriented perpendicular to a 1.5 Tesla magnetic field, meaning the plane of the loop of wire is perpendicular to the magnetic field. Then the loop is rotated so that its plane is parallel to the field direction in 0.20 seconds. What is the average induced EMF in the loop? So if you go back to physics 1, when you talk about average velocity, instead of the derivative of x with respect to t, it's the change in x, or delta x divided by delta t. And if we're talking about the average acceleration, it's delta v over delta t. So this is the same way, same thing. The average induced EMF in the loop is delta the flux, or delta psi b over delta t. So let's see if we can set this up. And so we are asked for the average induced EMF. So, and again, we're interested in the magnitude. And that's equal to n times delta psi b over delta t. And so what do we know? Well, we know that there's just one loop of wire, so n is equal to 1. We are not given the magnetic flux, but we're given the magnetic field, and we're given the diameter of the loop of the wire. So the magnetic field we know, and the area we know, or we can calculate. We also need to take into account the angles that are involved. So let's figure this out before we go any further. So initially, so we have B, and it's perpendicular to the plane of the loop. And remember, B makes an angle, or theta is the angle that B makes with a line that's perpendicular to the plane of the loop. So theta is equal to 0. And then finally, that's the plane of the loop. And B is now going straight across it. So theta is equal to 90 degrees. Again, you have an angle, the angle is with a line that's perpendicular to the surface. And so the cosine of theta in this case is 0, and the cosine of theta initially is equal to 1. So we can write this as n b times the area, which is pi r squared. And then the change is the change in the angle. So that's the cosine of 90 degrees, which is the final value, minus the cosine of 0. And that term is just going to be -1. So the cosine of 90 is 0, and the cosine of 0 is 1. So the term in parentheses is just going to be -1, and that's over delta t. And we're taking the absolute value, so we can write this as NBR, or NB pi r squared divided by delta t. And so n is just 1. B, we are given, it's 1.5 Tesla. Pi, we're not given the radius directly, we're given the diameter. So the diameter is 22.0 centimeters. That means the radius is 11.0 centimeters, or in SI units, 0.110 meters. And don't forget you're squaring that. And you're dividing that by delta t. And delta t, we're told it rotates in 0.20 seconds. And again, this is going to be in volts. So you plug all the numbers in. And you get 0.029 to two significant figures. Or, 0.29, excuse me, volts. So 0.029 volts, and so that's what's induced. So that's how you figure out the induced voltage. And so it depends, and you'll see a lab experiment with this, it depends on how quickly the magnetic flux is changing. So you'll see a little bit of this in the laboratory experiment. So let's get back to the lecture. Now, formally, Faraday's law is written without the absolute value signs, but with a negative sign. The delta V is equal to negative capital N times the derivative. And the negative sign is explained by what's called Lenz's law. And that an induced current will act to oppose the change in the magnetic flux that caused it. So what exactly does that mean? So let's say that the loop of the wire lies in the XY plane. If the magnitude of the magnetic flux is increasing, the induced current will create a magnetic field that points in the opposite direction to the Z component of the original magnetic field. And the Z component is the component that's either pointing directly into the XY plane or directly out of the XY plane from your vantage point. And if the magnitude is decreasing, the induced current will create a magnetic field that points in the same direction as the Z component of the original magnetic field. So if the magnetic flux is decreasing, then the induced current will create a magnetic field that points in the same direction. And so this goes back to the previous chapter. If you have an induced current, that induced current is going to create its own magnetic field. And that magnetic field will oppose the change in the magnetic flux that caused it, whatever that was. And so that's basically how that works. And so how do you figure out, well, the first thing you'll figure out is the change or the direction of the magnetic field caused by the induced current. How do you go from that to the direction of the induced current? Well, you use another right-hand rule, and it's basically the reverse of the right-hand rule for a solenoid or for a circular loop of wire. So you curl your fingers, rather you point your thumb in the direction of the magnetic field caused by the induced current, and your fingers will curl in the direction of the induced current. So that's basically how that works. So now we have an example, and you definitely want to refer you to your textbooks for this one. So this is problem number 2. The north pole of the magnet in figure 2936 is being inserted into the coil. In which direction is the induced current flowing through the resistor R? So let's see if I can reproduce this diagram reasonably well enough when we go to the whiteboard. So this is a qualitative problem more than anything. And we'll clear that. And so we have a bar magnet. And you'll see something a little bit similar to this when you do the experiment. So we'll set up a solenoid. We will hook it up to a galvanometer or to a current probe, so that you can see the current. And we're going to insert a bar magnet in. And you're going to determine, well, is the current that you get through the solenoid positive or is it negative? And why? And so it's more about the directions than the magnitude. The magnitude will depend on how quickly you insert the bar magnet or pull it out. The direction will depend on two things. One, whether you've got the North Pole facing in, and whether you're whether you're pulling it in or moving it in or moving it out. So this is the magnet, and so we have a coil that's looks something like this. Their loops are a lot smoother than my loops. But, so you don't have like an external power supply or anything like that. So the bar magnet is being inserted into the coil. Now, the North Pole is facing the bar magnet. So remember, magnetic fields point out of the North Pole and into the South Pole. So as the North Pole of the magnet is approaching the coil of wire, B is going to point to the right, at least B through the coil of wire is going to point to the right as it's approaching. And as it's approaching, the magnetic field is going to increase. So the magnitude is going to increase. So the induced current since the magnitude of the magnetic field is increasing, that means the magnetic flux through the coil of wire is also going to increase, which means the induced current is going to point in the opposite direction, or the magnetic field due to the Earth's induced current. So it creates its own magnetic field. That points left. You know what I'm going to do? I'm going to visualize this a little bit better, at least from my perspective. So we'll say we have a cylinder like that. Like that. And so we have the current that's going out and around like this. So you can see how it's coiling around, and I think that's a better way of visualizing it than the book does. And let's see if I can maybe bring this up a little further. And so you can see how that works. And in fact, better yet, I'll draw it like this. So you have the magnetic flux going into this opening. And so you have it coiling around like that. I think that's the best way of visualizing it for you. And so you're asked for the direction of the current through the resistor. So it's coiling, the current, or rather the magnetic field created by the induced current is pointing to the left. So you point your thumb to the left, your fingers curl in the direction of the current, which is into the board above and out of the board below. So it's into the board above and out of the board below. So it looks something like this. Again, doing the curl so that it points to the left. So it comes out, it comes down this way. So it's pointing to the left through the resistor. So the induced current points to the left across the resistor. And so that's how you solve that problem. The key is to visualize it correctly. And it's a challenge a bit. But again, you want to be able to visualize it so you can see what direction the current is circling through the coil, because that's how you solve the problem. So again, the magnetic field is pointing to the right and increasing. So the induced current is going to create a magnetic field that points to the left. And so you curl you point your thumb in the direction of that magnetic field. Your fingers curl in the direction of the induced current. And so that's into the board at the top and out of the board at the bottom. So you draw that direction and you figure out which way the current is then going. So that's how you solve that problem. So let's move on to another example. The rectangular loop shown in figure 2937 is pushed into the magnetic field which points inward. In what direction is the induced current? So the magnetic field only applies in a portion of the area. So let's take a look at this example, and you can look on through the book if you want. And this example is easier to visualize on the whiteboard. So you have your loop. You have an area here where the magnetic field is pointing in. Into the board. And so we're asked, the rectangular loop is being pushed into the magnetic field, which means the loop is being moved to the right. And so we're asked, in what direction is the induced current? So the area and hopefully some of you can see this without me necessarily writing it. Of the loop influenced by the magnetic field. The magnetic field itself is uniform. But as you're moving to the right, the area of the loop influenced by the magnetic field is increasing. So the magnetic flux is increasing. So if the magnetic flux is increasing, then the induced current is going to oppose the change. So the magnetic field points into the board. The flux is increasing, so the induced current will create a magnetic field that points out of the board. So again, once you have that, you apply the right-hand rule. So your thumb points out of the board towards you, your fingers curl in the direction of the induced current. And so that is counterclockwise from our vantage point. So the induced current goes around the wire like that. So the induced current goes in the counterclockwise sense. So now we're going to go to a phenomenon called motional EMF. And so basically what we have here is a conductor with a length L that's moving in the presence of a magnetic field. So what is going to happen to that conductor? So let's visualize this. So we have a conductor. And so we have a conductor, and the conductor's of length L. And it's moving with a velocity v, and we'll say for the sake of argument that b is pointing into the board. So what's going to happen? So remember, the electrons are free to move. And so it's a conductor. So there's going to be a magnetic force that's involved. So figure out the right-hand rule. You point your fingers in the direction of V, you curl them in the direction of B, which is into the board. Your thumb is pointing up, but remember we're talking about electrons, which are negatively charged. So the electrons accumulate on the bottom. So the electrons are forced downwards. So that's going to create an accumulation of negative charges in the bottom and a deficit of negative charges, or a positive side on the top. So basically, you've created a positive terminal and a negative terminal. You've created a voltage, a potential difference. And correspondingly, you've also created an electric field. So the electrons on the bottom are going to be attracted to the positive side. So as the electrons accumulate on the bottom, the electrical force gets bigger. So equilibrium is reached. when the electrical force is equal and opposite to the magnetic force. And so this is the more generalized version of the results, or simply, now how do we write that in terms of a potential difference? Delta V in the generalized form is the integral of the negative of the integral of E dot dl. Or you can write that as, given the negative signs, you can take the integral and it's V cross B dot dl. And so that's the generalized version of this. Is the motional EMF is equal to the cross product of V and B dot dl. So there's a cross product and a dot product involved in this. So that's the generalized version, or the generalized form of the motional EMF equation. So you, again, to summarize, you have a moving conductor exposed to a magnetic field. So the electrons get forced to one side. So you have basically a negative end, and where the electrons have vacated, you have a positive end. So you've created a potential difference. However, as the potential difference builds up, as more electrons accumulate on that one side, the electric force comes into play. They're going to be attracted back to the positive side, but so the charge is going to build up until you reach an equilibrium condition. So the equilibrium condition occurs when the electric field is equal to, the electric field vector is equal to V cross B. And writing that in terms of a potential difference, that potential difference is V cross B, or the integral of V cross B dot dl. And again, the electric force is equal and opposite to the magnetic force. And so that's what gives us this relationship here. In the special case where the velocity and the magnetic field are both constant and perpendicular to the conductor, then delta V is equal to B times L times small v. So capital V is the potential difference or voltage. Small v is the velocity. So that's, you'll need to keep those things in mind. So the simple example we're going to do here, you're going to be using this equation, but there's at least one example, I forget whether it's the recitation or the homework, where you're going to need to refer to this up top. So let's move on to the example then. So the moving rod, and it's basically what we've already drawn, is 13.2 centimeters long and generates an EMF of 120 millivolts while moving in a 0.90 Tesla magnetic field. What is its speed? So again, everything is perpendicular in this case. So it's the simplified version. So delta capital V is equal to B times L times small v, and we're asked to solve for the speed. So small v is equal to delta capital V over B times L. And so we are given that the EMF is 120 millivolts. If we want it in meters per second, we will write it as in volts. So that's 0.120 volts divided by B, which we're given as 0.90 Tesla. And then multiplied by, and then L is 13.2 centimeters long. Again, if we want it in meters per second, we'll write it in meters. So again, if you want your answer in SI units, you write all the variables in SI units. So writing it like this, and having everything converted into formal SI units, the answer that you'll get is going to be in meters per second. And so you get, we only know the answer to two significant figures, you get 1.0 meters per second. So as simple as that. And so that's how you figure that out. And again, that's if everything is perpendicular and nothing is changing over the length of the conductor that would require integration. So if V and B are uniform, you're not going to need integration, but you may the cross product and the dot product may come into play. So that's something to keep in mind. The integration only comes into play if V or B is not uniform over the length of the conductor. But if they're both uniform, you still need to take into account the cross product and then the dot product when you do this. Okay, so moving on from that, an important example of motional EMF, although you can also derive this relationship using Faraday's law, is AC generators. Now, AC generators are very, very important. The grid, our electrical grid, runs on alternating current. The things that, with the exception of solar cells, the things that supply power to the electrical grid, whether it's windmills, whether it's gas plants, coal plants, hydroelectric plants, whatever, they rely on, they generate AC power. So how exactly is that done? So either you have direct mechanical motion from hydroelectric or from windmills, or you have heat that gets converted into mechanical motion by burning coal or natural gas to convert water into steam. And then as that steam expands, it does work. But in all those cases, you're turning a coil of wire within a magnetic field. And as it rotates, its magnetic flux is constantly changing. It's constantly going from positive to negative. So it doesn't matter which side you define as positive and which side you define as negative, but as you're flipping it around, the sign is going to change. And as the sign changes, the direction of the current through the wire changes. So it shifts back and forth, and it does it sinusoidally. So the voltage across the coil of wire is a sinusoidally varying function of time. So how does this work? So let's say, and if you look at the diagram, you have a horizontal length L, or you basically have a rectangular loop, although this applies generally. It doesn't, the shape of the loop ultimately doesn't matter. But you have a horizontal length L, and your width is A in this rectangular loop. And so what happens is the magnetic field is pointing to the right. It's going across. So you have this conducting wire that's rotating or that's moving through the magnetic field. And so the magnitude of V cross B is V times the sine of theta. Theta here is the angle that V makes with B. And so you have V times the sine of theta, and so that's the angle, and then you're taking that angle, which is going to be perpendicular to both, so it's either going to, that cross product is either going to be into the page or out of the page, which means it's going to follow along the line segments BC and AD. So you're not creating a motional EMF through the segments of width A. but you are through the segments of length L. And so the induced EMF is equal to B, the magnetic field, times the length. Remember, we've got two segments of wire. So it's B times 2 times L times V sine theta. And again, because you're taking the cross product of V and B into effect. So, what?
Where's Mom?
Mom went out to Kohl's, and you're not supposed to open the door when it's closed. Close it, please. Okay, that was the share, not the recording. I apologize for that. So it's 2BLV times the sine of theta. That's the induced EMF within the wire. Now, if the loop rotates around its center with a constant angular velocity omega, so the angular velocity is just the axis is equal to V divided by the axis of rotation. And so V divided by R, or the radius of rotation. So how does that look? So V is equal to A over 2 times W. And you can write theta as being equal to omega t. It's rotating with a constant angular velocity omega. So theta can be written as omega t. V, the linear velocity, is equal to the radius of the rotation, which is A over 2. So remember, the axis is going through the center of the segments of width A. So it's A over 2 times omega. So you plug those in, and you see over here, you have the 2's cancel out. You have the magnetic field, and then you have the length L times the width small a. Well, that's just the area of the rectangle, and that turns out that that applies generally, so that you can write this as B times the area enclosed by the loop times omega, which is the angular velocity, times the sine of omega t. Now, if the coil of wire has capital N total loops, you can write the EMF as being equal to capital N BA omega times sine omega t. So think National Basketball Association. NBA omega times the sine of omega t. So that's the that's how you figure out the EMF, induced EMF in the wire. And so it's sinusoidally varying, so it goes from positive to negative. The maximum value is equal to N times B times A times omega. And you can also derive the same relationship using Faraday's law. So with that, we'll go on to another example. So the generator of a car idling at 875 RPMs produces 12.4 volts. What will be the output at a rotational speed of 1550 RPM, assuming nothing else changes? So, which means the area of the loop, the number of coils, and the magnetic field don't change, but the rate at which it's rotating does change. Normally, when you do these problems, you'll need to convert omega to radians per second. But here it's a proportionality problem, so you don't need to do that for this particular example. But let's go to the whiteboard. And so we are asked to find the output voltage, and it's not specified whether it's RMS or maximum, but it doesn't ultimately affect the problem. So what would the output at a rotational speed of 1500 RPM, assuming nothing else changes? So we can write this as delta V2 over delta V1 is equal to NBA omega 2 divided by NBA omega 1. So you're taking the proportionalities. And so the NBA terms don't matter. And it's just the omegas. And again, because there's a proportionality, we don't have to convert them to radians per second. So the delta V2 then is simply delta V1 multiplied, multiplied by omega 2 over omega 1. And we can leave these in RPM, or revolutions per minute. So we have delta V1 is 12.4 volts, and then everything else follows into place. So 12.4 volts. The final angular speed, so as you rev it up further, is 1500 RPM, and you're dividing by 875. So 15, is that 1500 or 1550? 1550 RPM. Divided by 875 RPM. And so you plug those numbers in. So that's 12.4 times 1550 times 8, or divided by, you get 22.0. You have three significant figures. 22.0 volts. So the greater the rotation in the engines, the more electrical power you're generating, or the car is generating. You might have noticed this, if you have the car on a hot day, that when you're idling, the air conditioner doesn't work as well, or the heat doesn't work as well. But when you've got the car cruising at a highway speed, the air conditioner is working just fine, or the heat is working just fine. So that's something, a little thing to keep in mind if you're driving, that typically, certainly with non-electric cars, if you're talking about a gas car, that the amount of electricity you're generating depends on the level, or you can generate, depends on the level of RPM in the automobile. So now we're going to get to a little bit of movie. You might have noticed as I put up the whiteboards that I have a web browser up. I'm going to show a film for about 10 minutes about why AC is the dominating source of the, how the electrical grid works. And it ultimately has to do with an invention called the transformer that was invented by Nikola Tesla, the person who the unit of magnetic field is named for. And he was a Serbian immigrant, but he did a lot of his work on Long Island, right here in Suffolk County, that he had a laboratory in Wading River up by the Sound. And that will hopefully someday soon, I've been saying this for a while, be opened as a museum. They've been working on it for a while, and I have no idea how much the pandemic has slowed things down, or how close they were before the pandemic. But it's been an ongoing process, but hopefully sometime soon the museum will open up. But here's a film basically explaining the key to AC power and why AC was necessary as opposed to DC for transporting electrical power over long distances.
You probably recognize this equipment as components of an electrical grid. You likely have something similar on utility poles in your neighborhood, bringing electricity to the homes and industries in your community. You may be interested to know that the technology mounted on this pole was at the center of an epic battle between the competing theories of the famous American inventor Thomas Edison and an obscure Serbian academic, Nikola Tesla. Tesla's theory won. Here's the story. In the late 19th century, Edison had become a household name, known around the world. His inventions and innovations covered everything from telegraphy and the movie camera to the phonograph and the light bulb. By the time he was finished inventing, he held over 1,000 patents. He was brilliant at not only innovating, but also at business. Edison turned his inventions into commercial successes. In the case of the light bulb, he created a complete power system, generating electricity and delivering it to customers, energizing their light bulbs. Edison's system typically used a steam engine to drive a generator, creating direct current electricity. This is an Armington and Sims steam engine. Edison purchased hundreds of these to turn his generators. Steam engines like this were fueled with coal, wood, or oil. This miniature steam engine demonstrates the process. In this working model, electricity heats water, producing steam. The pressurized steam is controlled by a valve system to drive the piston back and forth. A connecting rod from the piston connects to a crankshaft. This device converts the oscillating linear motion of the piston to a rotary motion, turning the flywheel. A valve controls the speed of the engine. This is a generator. Permanent magnets surround coils of wire. The coils rotate in the magnetic field, inducing a flow of electricity. In this miniature generator, the electricity flows through the filament of a light bulb. A drive belt connects the flywheel to the generator. Once it is up to speed, the filament glows. Electrical energy has become light energy. Edison's generators produce DC, or direct current. This means that the current, a flow of charged particles, usually electrons, always travel in the same direction, from one terminal of the generator through the load, in this case a lamp, to the other terminal of the generator. Battery cells also produce direct current. Electrons flow from minus to plus. Edison built hundreds of DC plants around the world. He realized that there was a huge market for electric light. But there was one technical problem he had not resolved. The electricity lost energy as it traveled through the wires. Once the wires from the generator exceeded 2 kilometers long, there was not enough electrical energy left to turn on a light bulb. Every customer had to be within 2 kilometers of the power plant. This phenomenon was called line loss, a serious problem for Edison. There was no obvious solution. Nikola Tesla, a Serbian electrical engineer, arrived in America in 1884. He brought with him the solution to Edison's problem. Tesla was an engineer and mathematician. He understood the science of the day, including Ohm's law and Joule's law, mathematical descriptions of the relationship between voltage, current, resistance, and power. Joule's law reveals Edison's problem. This simple formula, power equals current squared times resistance, tells us that the power lost when current flows in a wire is equal to the resistance of the wire times the current squared. Current is represented by the letter I and is measured in amperes. Resistance is measured in ohms, and power in watts. Most of the power lost becomes heat. The wire gets warm. As you can see, resistance in the conductor is one factor in line loss, but current affects line loss exponentially, I squared. Reducing current without reducing available power would solve the problem. There is a way to do this. We can rearrange Ohm's law to state that R equals V over I. Substituting V over I for R in Joule's law, we get this. Power equals voltage times current. Here is what this means. Low voltage and high current can produce exactly the same power as high voltage and low current. 100 amps times 10 volts represents 1,000 watts of power. 2 amps times 500 volts also represents 1,000 watts of power, with the advantage of a small current traveling in the wire. Edison knew that higher voltages and lower currents would resolve the line loss problem, but high voltages were dangerous. There had already been some deaths when experimenting with this solution. It was not possible to safely deliver electricity at 1,000 volts or more into homes. He had no solution to the I squared R problem. The solution that Tesla proposed, a solution rejected by Edison, was to abandon direct current and develop an electrical grid using alternating current, AC. Unlike DC, alternating current doesn't flow constantly in the same direction. It changes direction, surging back and forth. Alternating current is easily produced with a special type of generator, and AC has some very interesting properties. This surging back and forth motion of the current produces electromagnetic radiation that can induce current flow in adjacent but unconnected conductors. Tesla understood this radiation and perfected a device capable of changing voltage and current in an electrical system, the transformer. This changed everything. Suddenly it was possible to deliver electricity hundreds of kilometers using high voltage, low current transmission. The low current reduced line losses dramatically. The wires carrying the high voltage were suspended on towers at a safe height. The final step in this brilliant solution occurred when a step-down transformer converted the electricity back to a less dangerous low voltage with higher current for use in the homes and industries of the community. The relatively short distance from the transformer to the home meant that line loss from the higher current was minimized. Tesla had found a solution to the line loss problem. Edison realized he had a problem. His direct current systems were in trouble. He launched a bizarre campaign to discredit Tesla, even holding public electrocutions of animals to demonstrate the dangers of alternating current. But in the end, even Edison's wealth and reputation couldn't defeat the math and science. Tesla won. He solved the I squared R problem. You won't have to look further than your front yard to see Tesla's alternating current in action. This transformer in front of our house is converting the very dangerous thousands of volts on the supply lines to less dangerous 120 volts for use in our home. Alternating current electrical grids cover the globe, delivering power from a multitude of sources through an interconnected network of transmission lines and transformers. This is Tesla's vision of electric power transmission realized. Innovation with alternating current is just one aspect of this amazing man's life. Visit our Tesla website at hiloroad.com/Tesla to learn more about his accomplishments. And for additional science videos and projects, visit our website, hiloroad.com. Follow the projects link.
Okay, so the key was an invention called the transformer. So how does the transformer work? You have basically an iron core inside the transformer, and so you wrap a coil with N1 loops coming out of the input, or you wrap the input wire into a coil of N1 loops around the iron, and then you have a corresponding output wire that you're wrapping in a coil of N2 loops around the iron core. So what happens? Well, remember, iron takes on the magnetic field of whatever magnetic field is forcing it or is influencing it. So you have the input wire with a certain amount of current that's going to affect the magnetic field inside the iron. But as it's varying sinusoidally, that means the magnetic field and the magnetic flux through the iron are also varying sinusoidally. And what that's going to do is induce a current in the output coil. Now, the magnetic flux through both coils of wire is going to be the same. But remember from Faraday's law, the magnitude of the voltage or the magnitude of the induced EMF is also proportional to the number of loops in the coil. So what you wind up getting is a relationship where delta V2 over delta V1, the ratio of the output voltage to the input voltage, is equal to N2 over N1. So the ratio of the output coils, or the number of loops in the output coil to the number of loops in the input coil. So you have this simple proportionality relationship. So if you want to increase the voltage, you're going to have more coils in the output wire. If you want to decrease the voltage, you're going to have fewer loops in the output coil of wire. And the catch is that energy conservation requires that the total power coming in is equal to the total power coming out. Now, in an ideal transformer, energy is perfectly conserved. In practical terms, energy is very nearly conserved, but you might lose some energy in the transformer. But basically, power in, or I1 delta V1, is equal to power out, which is I2 delta V2. So basically, if you're doubling the output voltage, you're reducing the output current by half. And but the product of current and voltage remains constant. And so the basic structure of the grid is like this. You have the power supply. There you have the power generation. The first thing you're going to do is go to a step-up transformer that increases the voltage and reduces the current. And that makes it suitable for traveling a long distance. So you want to minimize the I squared R, the power that's lost over the wire. Now remember, a copper wire has a very low resistivity, but if you're talking about a really long length of wire, you're going to have a noticeable amount of resistance and a noticeable amount of power lost, but you can minimize that power loss by reducing the current. And so that's the key to this. And so the step-up transformer gives you a high voltage, low current, and then when you get into a residential area, you have a step-down transformer that reduces the voltage and increases the current. And so if you look outside at the power lines and you see a bucket with a wire heading towards your house, that's a step-down transformer. That's converting the voltage-current combination to something that is suitable for your house. And then the current is drawn through a plug. You put the plug into the socket, and so that draws the current into your appliance. There may be a transformer in your appliance that converts what comes out of the plug into a voltage-current combination that's more suitable for that particular appliance. So you may have transformers in a number of different places on the path from power generation to the appliance where it's ultimately used. So a step-up transformer means you're increasing the voltage. You're decreasing the current in a step-up transformer. A step-down transformer means you're decreasing the voltage. So delta V2 is less than delta V1. So we're going to finish with an example. A transformer has 620 turns in the primary coil and 85 in the secondary coil. So that's N1 and N2. So what kind of transformer is this, and by what factor does it change the voltage? And then by what factor does it change the current? So let's go to the whiteboard one last time. So we'll clear this up. So N1 is 620. And N2 is 85. Now remember, delta V2 over delta V1 is equal to N2 over N1. So if you notice, N2 is quite a bit less than N1. So the output voltage is going to be less than the input voltage. And so this is a step down transformer is what that means. So it is a step down transformer. So the next part of the problem asks, by what factor does it change the voltage? So delta V2 over delta V1 is equal to N2 over N1. So that's 85 over 620. And so you put those numbers in, and to two significant figures, you get 0.14. So it reduces the voltage by a factor of 0.14. So the new voltage is 14%, or the output voltage is 14% what the input voltage is. So then it asks, by what factor does it change the current? So I2 over I1 is, remember, the proportion, the product of current and voltage is conserved. So I2 over I1 is equal to delta V1 over delta V2. So if the current is, or the voltage is reduced, the current is going to be magnified. So it's going to be the inverse of what you got here. And so that is equal to 7.3. So the current, or the voltage, is 14% of what it was initially, but the current is multiplied by a factor of 7.3. So this is a step-down transformer. It increases the current. So again, this is not something you would have going from the power supply to the power lines, but you may have something like this going from the power lines into your house, or possibly from a wall outlet into, or rather from the plug into an electrical appliance. You might get this as a transformer like this. Again, just taking the current that's coming in and converting it to a voltage current combination that's more suited for the needs of the appliance. So that's the basics of transformers. And so with that, we are done with chapter 29. So the next lecture is going to be the last lecture. It's on chapter 30. It's not on all of chapter 30, but we'll get to that next time. So otherwise, thank you, and have a good day.